I was very lucky to experience one of those periods when mathematics was sort of developing completely together with an application area. I mean, that was something similar with physics and analysis in the 17th, 18th, 19th century. Something similar with computer science and discrete maths. I was sent to Germany when I was 16, East Germany, of course, to learn the German language. And I was rather bored, actually. And so I began to think, and I decided that graph theory should be like algebra, should have some more structure to it. So I began to think about how I would multiply two graphs, for example, and came up with a definition which turns out to be the strong product, it's called.
What do you think was the source of this looking down upon combinatorics?
It was true that combinatorics was relatively easily accessible. For some people, this meant that those who went to combinatorics were the lazy ones who didn't want to study.
What do you think changed this attitude?
You know, computer science came, and with computer science, I mean, it was an unquestionably important topic. And of course, graph theory belongs to the mathematical foundations of computer science. And when, for example, the notions of polynomial time, so P and NP came about, then graph theory was the first, essentially, or one of the first few topics where it really penetrated and it really redid the whole structure and taught us how to look at this.
One problem that I'm very interested to know how you came to think about it and how eventually the collaboration went was your work on the short vectors in lattices and then the application to factoring polynomials.
I think I had a Texas 59 calculator and I wrote a program on it to check these algorithms on maybe simultaneous approximation of root 2, root 3, and root 5. And then I tried all sorts of variations. I mean, whenever I had an idea, and then one seemed to be much faster than the others. And so it took me maybe a couple of weeks, and then I was able to prove that it indeed works in polynomial time. And then I wrote to Lenstra. He wrote back that in the meanwhile, he and his brother, Arjen Lenstra, have noticed that if you can do this, then actually they can factor polynomials over the rational field in polynomial time. And so we decided to write a joint paper. I mean, that's how it came about.
What are the most interesting problems for you, problems you tried hard to solve and you didn't, or you're still trying?
I mean, I now confess. I worked on Hadwiger's problem, got nowhere. I worked on the problem of trying to find a combinatorial algorithm for coloring a perfect graph optimally. I got nowhere.
We are on camera, you know.
Yes. I would like to understand the possible limits of extremal graphs. Fix a problem, extremal problem, and then how do the large extremal graphs look like? What is the template for them?
Why is this set of combinatorial problems one which we cannot make progress on?
Suppose that you ask Archimedes how to construct a regular seven-gon. He probably would have said, well, I think it's not possible, but I have absolutely no idea how to prove something like that. And indeed, I mean, it took almost 2,000 years, or about 2,000 years before it was proved that you cannot construct a regular seven-gon with ruler and compass. I expect something like that happen with P equals NP, so that somewhere somebody will develop some tools, I don't know, maybe in probability theory, maybe in topology, maybe in algebraic geometry, and those tools, at some point somebody discovers that they will just imply that you cannot compute a Hamiltonian cycle in a graph in polynomial time. I think it's one of the really crucial, fundamental open questions in the foundations of mathematics, whether randomization gives anything more powerful in a situation where all the data are given than just deterministic algorithms.
I thought it would be really interesting to hear your perspective of growing up in Hungary as a mathematical talented, what it was for you and what it was for other kids like you.
I was very lucky because mathematics education was very much in favor, both on the part of those who directed the education, and also students liked it very much. And so when I got to high school, then this high school just started a specialized class for mathematics and collected a lot of students who were good in mathematics. And so we got together, and that had some really fantastic created some really fantastic group of students and atmosphere there, which I think it was really what shaped my life for the rest.
So famous mathematicians were already involved with your education at the high school level?
Yes. So, for example, András Hajnal came and gave a series of talks about graph theory, or series of classes, I should say, so to high school level. And there were others. Pa Reves was a taught us probability theory, and some other people were, most of them were young, although, for example, Rózsa Péter also often came. She didn't teach a class, but she taught some kind of special clubs and math clubs. Erdős visited us a few times, and that was a great experience.
At least I know for some kids this continued in afternoons or evenings, or being mentored on a more one-to-one basis.
These all happened. So there were events at the school. Now also there were events that were maybe citywide or even nationwide, math clubs which we attended. Preparation for the Math Olympiad and other competitions. I really think that it was great. A very important element of this was just to meet other kids who were interested in mathematics. So simply the revelation that you can have other kids who are also interested in exactly the same kind of way of thinking and same kind of puzzles and problems and as you are, that was very great.
You mentioned competition. I know that Hungary is particularly big in competition mathematics, besides the ones that exist like the international. So can you tell us about this family of competitions in Hungary, and what do you think it does for the young mathematicians?
But this is a little bit controversial, and it's even controversial in my own mind. I think that some competitions are very beneficial because it allows students from different schools to meet and to concentrate on a particular study, and also it's somehow very stimulating to have competitions. Hungary has had a long tradition in competitions in mathematics. I mean, the first nationwide competition started in 1894, I think. So it had a long tradition. Also, there was this high school periodical, which I think is great. There I have no reservation.
The Comal.
The Comal, yeah, that's a periodical for high schools. It's also started in 1893, maybe. So it's a very old one, and this has monthly problem sets that the students can send in, and then there is some kind of grading and competition, which at the end of the year winners are announced. The picture was printed in the periodical. Nowadays, to have your picture somewhere is sort of nothing, but in those days that was somehow part of the attraction of this. And another competition which I am somehow less hesitant about saying that it's good is we have a competition for university students, which is called the Schweitzer competition, which goes on for 10 days. Students get 10 problems at the beginning, and they can go home, they can go to the library, they can search the internet, whatever they want, and at the end they have to send in as many solutions as they can. So it's a little bit research-like, and indeed some papers grew out of solving some of these problems. So this I think is a quite interesting thing, and I am happy that I had a chance to take part in it when I was a university student.
From your answer, I expect you don't think quite the same about the more standard competitions where people sit in a room for 2 or 3 or 5 hours and have to come out with it.
I mean, I have nothing against it. It's the question is the number of them, and I think recently they have just become too numerous. I mean, there's of course the International Mathematical Olympiad, and there are sort of certain nationwide competitions for the selection of the team, and then there are others which are similar but independent of this. Some historical reasons they are separate. So I think it's a little bit overdone these days, but.
I was thinking about a different aspect. To what extent do competitions repel mathematical talent of kids that are simply not into competition? Do you know of examples, or do you think similarly about that?
I think I certainly have examples of mathematicians who were not good in these competitions, and they became very important mathematicians later. This does not necessarily mean that the competition is bad. It's just that you should not consider it as the only measure of mathematical talent.
And this is a message that you get from the educators, that this is not the only way to, as a young...
Actually, I must say that when I was young, there was a little bit more emphasis on other mathematical activities, like where competition. Well, I mean, everything. I mean, for high school kids, somehow everything is organized as a competition, but because you cannot give degrees. I mean, so why would anyone work? But we had things like writing an essay or something on a mathematical topic, maybe 30, 40 pages, looking for proof. So it's a little bit like an activity like it would be maybe a junior thesis or something in these days. Now that was good. Somehow nowadays, because the number of competitions have increased, they have less time for doing this kind of activity.
when I first started meeting Hungarian mathematicians, it struck me, I knew of course of the competitions, but what is one thing that struck me, I think, is that they praise each other to a degree that I don't see in any other community, mathematical or otherwise. So it somehow stands in contrast to the competitive, to the competitions. So how can, well, I would assume you agree, but can you describe what this grows out of?
It's always difficult to, without actually measuring whether this is really true or not. I remember periods when the mathematical community was bitterly divided and people said all sorts of bad things about each other. Maybe not internationally, but at least at home. One thing is true that in the class, in my high school class, where there's a lot of competition with some really outstanding other students. We remained very good friends. So there was, for example, a competition in TV where you could, where the students, I mean, in the final, the 8 students who made it to the final, they were paired up, and then we were sitting in some glass cages so that we don't hear each other, and we got the same problem, and then it was a live TV show. I mean, it was in the 60s, so TV was maybe for 2 days or 3 days a week. So this was one evening program. And so we had to solve these problems. We had 3 minutes to think, and then and it was a popular program in those days. And I was in the semifinal. I was competing with Lackovics, and in the final I was competing with Pósa. They are both great mathematicians, and it was a tough fight.
You won.
I won, yeah, but just barely. Lackovics was ahead of me until almost the last question. Somehow I won, but we remained very good friends. I mean, somehow we managed to put it aside, and I mean, it was something that you were not supposed to take that seriously.
So who were the influential figures for you as a young mathematician? Who did you look up to and wanted to be like?
Paul Erdős certainly was a fantastic person, and I was maybe 15 or so when I first met him, and I was introduced to him by Pósa, who was a classmate of me. He started doing mathematics very early, at the age of maybe 13 or something, and he had a couple of joint papers with Erdős by that time. The graph theory was just beginning to be developed, and so there were lots of open problems, and some of them are still unsolved, and some of them could be solved in one afternoon, and you couldn't know in advance which problem was which. So it was a very appropriate for young people to try to do something and solve some of these problems. And I solved one of the problems that Erdős posed. It turned out that by that time, a bit earlier, somebody else also solved it. So it was, I mentioned as a footnote in the paper, but that allowed me to go and attend some, I don't know, maybe one can call it a session. So what happened was that Erdős visited Hungary. He just started to come to Hungary in those days, because before that, in the 50s, he didn't come. And he stayed in a hotel, and he was sitting in the lobby of the hotel more or less whole day. And various people came and were just hanging around him. And he was having a conversation with maybe 5 people parallel. telling them problems, maybe commenting on the joint paper, what should be deleted, what should be added. And we were, when we had the time, maybe it was school break or something, we were sitting around more or less the whole day. It was a side benefit that Erdős, when it was lunchtime, he invited everybody who happened to be there for lunch. And but irrespective of this, it was very, very interesting and very exciting. In these sessions. I was then introduced to Tibor Gallai, who was, in a sense, just the opposite of Erdős, a good friend of Erdős, but he was a very, very shy person, very, very. He didn't like to go out, never went to conferences, but he had a great knowledge, and so he taught me a lot of the technical side of graph theory, and a lot of other subjects that he thought that was useful for somebody who wanted to do graph theory. Told me about linear programming and other things like that, which were all very new in those days.
So this was private sessions? Or
These were private sessions, yes. I usually visited him in his home, and then we had an afternoon, and he told me lots of questions and problems and methods and everything like that.
And Paul Turan and Vera Schoch were also involved in this mentoring?
Yes, although I did not have this kind of sessions with them. They were teaching at university, which was a different kind of contact with the students. So I did take a course, introductory analysis course from Vera, and she did have some additional seminars and special classes. So in a sense, she was also quite involved with teaching, extracurricular teaching, not on one-on-one basis.
You mentioned you solved some problem of Erdős. This was the first research problem you solved, or this was don't consider?
I don't consider this as.
So what was the first one?
I was sent to Germany when I was 16 in the summer, and the summer break I was sent to Germany, of course, East Germany, of course, to learn the German language. And so I was with some other young people, and I was rather bored actually. And so I began to think, and I decided that graph theory should be, like algebra, so somehow should have some more structure to it. So I began to think about how I would multiply two graphs, for example. Came up with a definition which turns out to be the strong product. It's called the strong product today. And so I thought that one should decide, with a product, one should decide whether you can cancel. So when A times B is equal to A times C, does it imply that B is equal or isomorphic to C? I started to think about it and eventually came up with a proof, which was actually rather complicated induction. And then I was thinking about it, what is behind, and then I came up with an explanation for the proof, which was that, the proof I counted subgraphs, various subgraphs. And then it took me about a year until I realized that you should not count subgraphs, that you should count homomorphisms or maps. And then all of a sudden things become much clearer because these functions are multiplicative. And so I proved this. It turned out to be that the problem was asked earlier by Tarski, but it was not answered. So when somehow he got the news, it took a year or two, but then he was quite enthusiastic about it, and he invited me to a meeting in Oberwolfach. So it was a good thing, and it turns out actually that this counting of homomorphisms, identifying a graph by specifying the number of maps from other graphs into this graph, that came up again recently, and it led to the graph limit theory in my recent research. So somehow, for a long while, it was sort of not really that active, but then it became again.
We can talk about graph limits. It's, of course, a very active field of research for you and for a huge and growing mathematical community. So can you say how it started again? And
I was at Microsoft Research, and Jennifer Chase came to me with a question, which was more or less that they were looking at internet models, and which were just after Barabási Albert's papers. They were becoming a popular subject, and she asked that suppose that this graph grows to infinity. These are about growing. These are rules that describe how a graph is growing. And she asked, is there a notion of something like a law of large numbers or a central limit theorem, but not for numbers, but for graphs, for randomly growing graphs? And then I remember this old paper of mine, and I saw that this gives a possibility of defining when we want to consider such a graph sequence convergent, if these homomorphism numbers from every fixed graph appropriately normalized would converge. And so we began to study this definition.
so basically it's a reduction from whether a sequence of graph grows to whether a collection of sequences of real numbers
grow,
converge,
and for those the limit is defined, and so you can define it like this. And then it sort of, by a strange coincidence, Mike Friedman, who was working on quantum computer, he's working on designing a quantum computer based on topological principles. He asked the question, basically it's that how can you recognize that a function defined on graphs, so a graph parameter, whether it is the partition function of some model. So you only know the value of the function on each particular graph, and can you define, under what conditions can you define a statistical physical model that would produce this partition function. And it turned out that these homomorphism numbers were, again, just right for giving such a characterization. And with Lex Schreiber and Mike Friedman, we found this other theorem. And then from then on, there are two theorems. There are so many ways to try to understand the connections between them that this led to the development of this theory.
So was it essential from the beginning to have something like the Semeredi regularity lemma to understand these graph limits, or was it only later?
It took a while to realize, maybe half a year or so, that the regularity lemma is actually a central tool in this study. So we first didn't quite realize this, but then at some point, actually when we discovered that there is this simpler version of the regularity lemma due to Fries and Cannon, that was the one which we really needed, simpler but tighter version, and so we were using that. Then we discovered connections with lots of other things. For example, property testing in computer science, which has been a well-developed branch or theory, and which turned out to be, again, very closely related. And also there was a parallel theory. This was about dense graphs. There was a parallel theory for bounded degree graphs, which was developed by Benyamini and Schramm. Schramm was just next door at Microsoft Research. It took maybe a year until we realized that we were working on two sides, not equivalent questions. They are.
Can you say to what extent is the status of the graph limits questions now, or the graph limits theory, close to analysis? So at which stage in the development of analysis are you with the graph limits?
So far, this graph limit theory has produced a lot of interesting connections with various branches of mathematics, with algebra, with analysis, measure theory, and so on. Applications in computer science and extremal graph theory and so on. So I believe it's going quite well. But I have had experience with some other research topics where at the beginning it looked like, oh, that's a beautiful theory. We'll be able to get many, many things. And then at some point it turned out that this is how far you get.
My understanding is that things that the limit objects are continuous objects as opposed to the sequence itself, which is composed of discrete structures. So in the limit, some algebraic structures arise sometime which are not present in the discrete structure. So can you say something about this or give an example of where it can be useful?
One thing where this theory is useful is that it allows you to ask, as to state in an exact form questions like what, for example, in extremal graph theory, what kind of extremal graph problems, whether they have a solution, or how does the solution looks like. These are sort of undefined questions, but with graph limit theory you can give a precise meaning to them. In some cases they are solved, and in some other cases they are maybe not solved yet. But you can at least state a clean question and work to try to find an answer.
So what is an example of an interesting analog of an interesting transcendental number like pi in this? Is there?
I don't know about pi, but certainly there are some analogs of maybe algebraic numbers, and those are those graph limits which can be defined in a finite way by a finite number of conditions.
As a probabilistic model or as a...
Say I prescribe the density of certain subgraphs in them, and in some cases this uniquely determines such a limit object, which is a function, continuous object. And the point is that these are exactly those which, I mean, this is a conjectural, but we have a conjecture that these are exactly those which describe you the possible templates of extremal graphs. So suppose you have an extremal graph problem. Find the maximum number of 5 cycles in a graph conditional on, I give you the density of edges and the density of 4 cycles, something like that. And then the graph gets very large, and the question is, how does the extremal graph look like? And graph limits allow you to state this, that what is the limit and in the limit it has a much simpler structure. And we believe that these limits are exactly these kind of algebraic objects in this setting. And there are also conjectures about how they should look like. And I think that gives us some research program for a few more years at least.
Obviously, it connects to areas of math like algebra and analysis and probably geometry. Are these communities interested? Are they connecting more to combinatorics through this bridge?
I hope so. I think it takes time, but there are some interesting developments. Lex Schreiber, for example, proved a very nice theorem in tensor algebras, which the experts in the field thought it would never be true. It cannot be true. But from the graph, generalizing the graph approach, he managed to prove this. Also, there are, I think that there seem to be connections with ergodic theory, which I not yet worked out, but they are clearly there. And there are some interesting new norms that come up on function spaces defined by graphs, and at least some functional analysts are interested in them. So I think it probably has some impact. In probability theory, it's even more. So it turns out that Varadhan, Chatterjee, and Diaconis have used this graph limit theory in a quite non-trivial way to analyze some large deviation, to prove some large deviation theorems for random graphs.
The relationship of the mathematics community to combinatorics, to discrete mathematics, how it has evolved in this, 40 years or so.
Hungary was, of course, strong in this area, and well, there were, one could hear even in Hungary some voices saying that this is not a serious thing, and I got advice to try to do something more serious instead.
By whom?
Oh, by some analysts. But all in all, it was an accepted area because many leading mathematicians, including those who eventually did other areas like Turan or Hajós, they also had papers in graph theory, so they were not against it. But worldwide, it was not considered to be a serious subject, and I think Erdős was often criticized or even looked down upon for his role in the development of this field. I remember when I was in the University of Chicago, that was in the mid-80s, around 85. MacLean organized a seminar with the title Erdős is all wrong. And he set out to prove that mathematics, that kind of mathematics is worthless. I don't think he managed to prove. In fact, he organized a public debate.
Who was against him?
Laci Babai and me. And I had the feeling that we won the debate, but I don't think we convinced him that.
So, but it's interesting. So, how did the debate? What did it consist of? I mean, I don't see that anybody can prove that.
So he challenged us to bring one result that we think in graph theory, which is a significant result in graph theory, and he will prove that it's not significant. So we had to give him in advance what we want to talk about, and he prepared. And Lancy Baba, he brought some result in about automorphisms of graphs, and I don't quite remember that part of the debate. And I brought the Robertson-Seymour theorem.
It was already 85.
Wagner. Well, it was announced. It took 20 more years to publish all the details, but the basic result was already announced, and there were sketches of the proof, which made it quite likely that it's true, and that how the proof would go. And so I brought this up, and he was trying to prove that this was a kind of insignificant extension of Kuratowski's theorem, which is absolutely wrong. I mean, it's the deepest theorem in graph theory, and whatever it inspired is amazing and breathtaking. So I think I could convince him, or the audience at least, that this was not so, that this was an important theorem.
So what do you think was the source of this, looking down upon combinatorics in the general eyes of is are specific people to blame, or?
I don't know. I mean, there are probably several. One is that it was true that combinatorics was relatively easily accessible. There was no big body of knowledge that you have to go through and that you have to digest before you can do anything. And for some people, this meant that those who went to combinatorics were the lazy ones who didn't want to study. And actually probably there were indeed. This was indeed the case in some cases. Also, there was a lot of very, very bad literature published in graph theory, because it was easy to publish in it because there were people in other sciences were already at that time interested in this notion, because the chemists and maybe some biologists and sociologists were interested in graphs, because they needed it at least as a language to describe certain structures that they were studying. And so people could easily write papers that were nothing but explanation of introducing some definition and proving the absolutely trivial things about them. And of course, if you just see these, then you don't realize that the other half is hard work, and often you do have to learn things because you want to apply them in graph theory, and you want to make graphs, to solve problems in graph theory that it's not elementary to solve them. You have to apply some tools from other branches of mathematics.
Do you think it's essential for something to be interesting that you apply other tools, or that you have to work hard for?
Not necessarily, but I think eventually it comes to that. I mean, if it's a big theory, maybe the first concepts and first proofs are relatively easy, but eventually it sort of seems to integrate with mathematics. And it's also true that in those days, mathematical fashion was more in the direction of generalization, abstraction. I tried to, when I was a student, I worked somewhat in topology, and I proved some results that I liked, and about planes, and so very concrete structures. And but then half of them turned out to be known from the 20s, but everybody forgot about it. So just by accident, discovered that they were already done in the 20s, actually by a Hungarian mathematician, Keréki Artó, so it was embarrassing even more. And the other half turned out to be that nobody cared. I went to some conference in topology, and I gave a talk about that, and the chairman was the only other person who came to the talk. So it was very, very disappointing. And so I think it was because everybody was fascinated by case theory, general homology theories, and some kind of general scheme of things. And this was about rather down-to-earth topological results about the plane.
What do you think changed this attitude? I mean, so there was some evolution, and it seems like the attitude of the general math community towards discrete math, grew more and more favorite. So was it certain results or certain people, or how do you explain the change?
There were some people who were well established in mainstream mathematics and who did work in combinatorics or graph theory, like Giancarlo Rota, for example. I read his papers a lot, and I really was. He was one of these people who showed me through his papers how to make connections with algebra, with measure theory, and other classical mathematical areas. Also, computer science came, and with computer science, I mean, it was an unquestionably important topic. I don't know if people thought it to be sort of important for mathematics, but it was important. And of course, graph theory is the mathematical foundations or belongs to the mathematical foundations of computer science. And when, for example, the notions of polynomial time, so P and NP came about, then graph theory was the first, essentially, or one of the first few topics where it really penetrated, and it really redid the whole structure and taught us how to look at this. So I remember that before that, a few years before that, so maybe in the late 60s, I mentioned Tibor Galai, whom I had long sessions. So during one of these sessions, he explained that there is the problem of whether a graph has a Hamiltonian cycle, and there's also the problem whether a graph has a perfect matching. They said, well, this perfect matching problem is well understood. It has all sorts of... He was not maybe so much into algorithms, but he said there are all these necessary and sufficient conditions which are perfectly answering all reasonable questions about this one. But there's this Hamiltonian cycle problem that looks almost the same. It's just a little bit different. And we don't really know how to approach it, and there are really no general results about this. And with some friends, including Pósa and also Peter Gács, we started to think about this. What could be how can we actually maybe explain this difference? And we were trying to use the Kolmogorov complexity theory for that, but we didn't get anywhere, which was around by that time.
You didn't know about Edmonds' paper at the time?
We did know about the Edmonds' paper, but didn't quite, we didn't quite look at the philosophy behind it. So, and then I came to the US I had a year that I spent in the US. Got a stipend from actually Vanderbilt University, but then I also visited Jack Edmonds in Waterloo, and there was also some conferences, and so I learned about P and NP, So I went home and I met Peter Gatch, and he spent the same year in Moscow with Kolmogorov. And so we met, and then we tried to tell each other that now we understand what the difference is, because he learned about Leonid Levin's discovery of basically the same fundamental ideas here. And so that is how we learned about this, and it was immediately clear that this changed the whole graph theory, but also it somehow made graph theory part of a much bigger project, which is computer science. And I think that also, I mean, of course, P equals NP also penetrated a lot of other areas of mathematics, number theory, group theory, and others. And so somehow, yeah, by 2000, it made it to the Millennium Problem. So it's really has been recognized as a fundamental question of our times, and somehow its connection with graph theory, the basic examples are from graphs also, I think contributed to the fact that graph theory is now accepted.
Yeah, this seems to have come much later. I mean, I think in the beginning, theoretical computer science, because its connections to discrete math, it's obviously of a discrete nature, was clogged down with the combinatorics and discrete math as something lowly, maybe, and it took some evolution.
That's definitely true, and I think actually that the potentials of this making more connections with classical mathematics are still there. They are not exploited at all. Graphs and combinatorial structures provide interesting algebraic varieties, they provide interesting groups, they provide interesting algebras and interesting examples for almost everything. So nowadays, I think it's accepted that it's a part of mathematics that is honorable.
In some sense, I think it was always there as like what you mentioned, examples of algebraic structures, of varieties that arise from these. And moreover, I think combinatorial tools were always used by certainly number theorists, analytic number theorists. So it seems they all knew that they were using combinatorics, but somehow never acknowledging it.
The way I like to look at it is that mathematics is not really about discrete mathematics or continuous mathematics. There are some phenomena which we would like to understand, maybe sometimes in physics, sometimes in elsewhere, and they can be modeled by a discrete structure, or they can be modeled by a continuous structure, or they can be modeled by both, and then you go back and forth. As an example, maybe diffusion is a phenomenon, and you can model it as a random walk on a graph, or you can model it as a heat equation, a differential equation, and probably ergodic theory also tries to model the same thing. So there are various models, and it's good if these models talk to each other, because one thing that is discovered in one might actually be quite useful. Some ideas might quite be maybe not that naturally occurring, but eventually prove to be useful in the others.
Can you tell us about some of the results you had in which tools from a completely different area of mathematics is brought into a proof of a blatantly combinatorial theorem?
I always thought that this would be an important progress in combinatorics if this was done. And I was happy when I discovered or sensed that something like that was doable. Topology, actually my first application of topology was not to graph theory was not the Kneser conjecture, but a theorem which was a question of conjecture von Dasch-Frank. It said basically that if you have a graph and you want to cut it into, say, 7 pieces, and you prescribe the sizes of the pieces, and you also want that these pieces be connected, and the graph is 7 connected, then it can be done. And if you look at the case with 2 instead of 7, then it is easy to see that it's a kind of continuity argument. You start with putting everything on one side, and then you move the nodes one by one over to the other side, and you just have to show that you can do this. If you do it in appropriate order, both sides remain connected. So this is like the Bolzano theorem. You move from negative to positive, then every value in between will be attained. And so the idea was that maybe if you want to cut it into 3 parts, you have to come up with a 3-dimensional version of the Bolzano theorem, which is basically the Brouwer fixed point theorem. So I came up with a proof applying Brouwer's fixed point theorem here. And then maybe a year later or so, I heard about this problem of, or began to think about this problem of Kneser graphs and their chromatic number. And there was a paper by Erdős and Hajnal where they were constructing graphs with which had high chromatic number and had no triangles or even no short odd cycles. And they mentioned 2 examples. One were the Borsuk graphs, which come from a sphere connecting points which are almost diagonally opposite. And the other example were the Kneser graphs. And Miki Simonovic pointed out that these graphs, the Kneser graphs, are similar to Borsuk graphs. And so I thought maybe they are not only similar, but they can be, their high chromatic number can be proved by the same topological methods, and that's how the Borsuk graphs are, of course, topological by nature. So the Kneser graphs were discrete, but somehow one can construct an appropriate topological space. And then later, Imre Bárány simplified the proof where he actually made it even closer. Actually placed the points on a sphere and applied some variant of Borsuk's theorem. This is how this topological question came in. And of course, once you understand that there is some connection here between topology and graph theory, then you can go on and generalize it and notice that this kind of bound cannot be only given for coloring, but it can be actually a way to proving that certain homomorphisms don't exist and so on. I think once the connection is established, you can easily generalize it.
Right. So here you had a hint in the Erdős paper. So what was for you the most, I don't know, or for the people around you, the most surprising application of mathematics, non-discrete, to a combinatorial problem?
Certainly this topological theorem was well received. There was, I think, maybe another one was the bound on the Shannon capacity. You want to prove an upper bound on the size of a certain code. And so for this, you have to basically develop a way to prove an upper bound for the independence number of a graph, maximum number of independent nodes, which would be multiplicative or submultiplicative with respect to direct product. And I was trying to use linear algebra for that. Well, it took a while to figure out what the right notion was. I actually talked to somebody in functional analysis because I was trying to to use dimension arguments, which were by then quite well established. So I was trying to find some kind of linear structure representing the points by some vectors, and then trying to
representing the colors or
maybe representing the vertices of the graph by vectors, and so that the independent sets would correspond to maybe linearly independent vectors, and then somehow get it in a small dimension, and that would give an upper bound. That doesn't work. Actually, it works. I mean, it's a method by which you can obtain bounds here, but it doesn't give a strong enough bound in the case of the Shannon capacity of the pentagon. And so I asked the function analyst, how do you find a good estimate? So I thought that maybe instead of vectors, maybe one should attach subspaces of some space. And so how do you see the dimension of this subspace if it's in an infinite dimensional space? And then he said, well, I mean, usually it's measured by projecting some unit vector on it and seeing how long the projection is. And so I began to project unit vectors on my representing subspaces. Then I realized that you don't need subspaces, you can fall back on vectors. And so I somehow got the idea of trying to represent a graph by vectors, and then take a unit vector and project it on these vectors. And if you can do it so that these projections are long, then you cannot have a very large independent set of the graph. And I still remember that of course the question is whether the bound this gives is good, and it's not so easy, so I used a calculator. It was early days of calculators. And so I used a calculator, and when I got the correct answer is square root of 5, and when I got 4 digits of square root of 5 right, then I was very happy because then I trusted that the answer is square root of 5 indeed, and that was not hard to prove then. This then turned out to be sort of one of the first applications of semi-definite optimization.
Yeah, exactly. Yeah. So I was wondering how you see this baby of yours develop. I guess there was some dormant period. So this is an obvious relaxation. And then I think the next time it appeared is in the Gomast-Williamson paper approximating max cut. So, but I heard, is it true that you suggested to them to use semi-definite relaxation?
Well, semi-definite relaxation was at that time already, for their problems, the max cut problem, was already used by Randall and Poljak, so they developed formulas for max cut or bounds on max cut. My role was that organized a workshop in Princeton. Was maybe 91 or so. There was a combinatorial optimization year at DIMAX, and I organized a workshop about uses of this kind of method. I don't remember what exactly the name of the workshop was, and I don't know whether it was because of this or not, but I certainly would be very happy if that workshop contributed to the Gomast-Williamson result.
So by now, this methodology of using semi-definite programs, maybe as opposed to linear programs, to approximate combinatorial optimization problems is very developed, and in some sense it seems like a magically universal algorithm for it achieves the best possible for lots and lots of such optimization problems. So you find it surprising? You find it natural?
I think it's, well, of course you read about those problems where it gives the optimum, and you don't read about those problems where people have tried to use it, like I tried to use it in other problems, and it doesn't give the optimum or doesn't give anything reasonable. But I agree, it's a method which is clearly a lot more powerful than linear programming in many situations.
Constraint satisfaction problems, it seems, well, assuming something, it seems to always resolve optimally, basically. And this is a very wide class. I mean, just Max Cut is a first example of...
Yeah, that's a nice development, I must say. Because Gomans and Williamson contributed the important step of how to extract from the semi-definite relaxation a good approximation for the real unrelaxed problem.
How to round.
How to round, in other words, or how to make it integer, so how to round. That was, I was not concerned with this in the Shannon capacity paper. It was, I don't even remember whether it occurred to me that this could be used to round, but certainly did not. I think we attempted to use this when we wrote the book with Grötschel and Scriver on combinatorial optimization, where this method is applied to find, say, the chromatic number of a perfect graph. And we were trying to see if the solution to the semi-definite optimization, whether it directly gives a coloring, but we could not. So we just have some very down-to-earth and inefficient way of applying semi-definite optimization to subproblems repeatedly, and this way determine the coloring.
This is related to the book with Scriver and Grötschel brings up another baby of yours, which is the semi-definite hierarchies, which again, I think, I don't know exactly how much happened in the combinatorial optimization domain, but had a great rebirth, and today seems to be a very powerful optimization tool.
That was an idea that was around for quite a while. So in '79, Lex Scriver spent a year in Szeged, where I was professor, and we shared an office because office space was very, very limited, and we worked on lots of things together. And in particular, that's when we started to do the topic about kind of general algorithmic theory for convex sets and its applications to combinatorial optimization. And in particular, we actually formulated this idea with I think it was actually Lex's idea, that you could do this, apply this method, this relaxation method, to any combinatorial optimization problem. And then we couldn't find any example where it would give anything interesting, and therefore we just left it at that. And then a good 10 years later, we somehow, in Oberwolfach we met, and we were chatting, and we said, well, we should have another look at that. And then that's when we started to develop this repeated relaxation method.
So you mentioned this meeting Scriver in Oberwolfach and meeting with other people on your travels and starting out conversations that led to results. What do you think is the importance of these meeting places and travel to conferences, and as opposed to the toll they take in organization and time, etc.?
I think that personal meetings are very important still. I mean, certainly it was very important for me in the old sort of communist times, because to go and meet people was always very exciting and gave lots of new ideas. But nowadays, of course, there are so many travels and so many conferences that. But almost always after a conference, I feel that I learned something. It's something interesting. New people are doing things that are remarkable, that I should learn more about. The Oberwolfach, for example, is one of these really traditional conference centers that I was very lucky to be able to attend it in 1968 when I was a university student.
So you got permission to...
Alfred Tarski, I mentioned that I solved a problem of his, and so he invited me to a conference he organized in Oberwolfach. Now, that was not so simple. I had, of course, to apply lots of months and months in advance to get a permit to travel. And among all the Western European countries, of course, West Germany was particularly difficult to get permission for. And indeed, my request was rejected. And even an explanation was given. Explanation was that this is an important meeting and we cannot afford that a mere student represents the country. I don't know if somebody else wanted to go or whether it was just somebody's idea of how to reject it. And then Paul Turan went to the minister and argued that it's indeed doesn't happen too often that a student is invited to Oberwolfach, a second-year student, but exactly because of this they should allow it. So the permission eventually came a few days before the meeting started. I still had to get a German visa, which luckily I got in a day. And then I had to buy airplane ticket, and at that time it was possible to buy airplane ticket for foreign, so that was fine. And I could even buy the train ticket from Frankfurt to Wolfach. But I still needed some money because at that time I needed a bus ticket from the airport to the train station in Frankfurt. And I also needed a bus ticket from Wolfach to Oberwolfach. And the total was 10 Deutschmarks. And looked impossible to get the permission to take 10 Deutschmarks with me, except that my father, who was a surgeon, he operated the vice president of the National Bank before, and so we went to see him, and he had the right to give special permit up to 10 Deutschmarks. So I got 10 Deutschmarks, which just barely took me to Oberwolfach. And it was already on Tuesday when I got there because all this took extra days. But it was a fantastic experience and to meet people, talk to people, hear what they were doing. It's very, very interesting. I'm terribly happy that I eventually managed to get there, even if only for half of the meeting.
You were recently president of the IMU, of the International Mathematical Union, for 5 years. So what kind of, so I don't know even if this is part of the job, but does the IMU try to develop institutions that will enhance the experience of mathematicians, or maybe the opposite, close down things that existed for a while but are not serving their purpose?
Of course, the IMU has very limited means to do anything. We cannot run a conference center. One of the main tasks that while I was president that the IMU had to do is to find a permanent office, because before that the IMU was kind of a floating body. It never, the office was wherever the secretary was, and that unfortunately doesn't work. I mean, for example, it's almost impossible to have a bank account under these circumstances nowadays, because again, because of all this money laundering and other anti-money laundering laws and anti-terrorist laws. But also the activities are now much more widespread than they were maybe 20 years ago. There are many more programs in developing countries. So in developing countries, the IMU really tries to organize schools, conferences, events, maybe sometimes doctoral programs and so on. But so eventually we found a permanent office, which was one of the main tasks I had to do.
Another main thing you organize is the international meeting every 4 years.
Well, I mean, yes. I mean, the main role of the IMU, at least for the most visible, is that we organize the International Congress of Mathematicians every 4 years. That's when actually the president is then, a new president is elected, and new leadership is elected. And so this time it was in India.
What's interesting in politics of mathematics? What interesting things did you learn, or what fights did you have to resolve?
I must say that as far as conflicts went, there was very little. So mathematicians are good in cooperation, I found. So there was. I heard that there were tensions between our Math Education Commission and the research mathematics leadership, but that disappeared by the time I became president.
Over what?
I think it's mostly over the independence of the math education from. So some people wanted to make it more independent, less independent. There was some struggle, but I think we managed to sit down and clarify these, and I think the relationship now is much better. There is some ongoing and problem which is creating more and more discussion is about publications. I mean, it includes the problem of the price for journals, that it's going up at an enormous rate, and it's more and more difficult to have your institution subscribe even that fraction that is interesting. And then also about the quality, about this. There is a lot of question about numerical indices for journals like impact factor and others, which mathematicians don't like. It's not invented to measure the real quality in mathematics. I have no. I don't really know whether in biology or chemistry, how correctly it reflects the quality of maybe a journal, what its impact factor is. But in mathematics, it's definitely not an important way of measuring the quality of a journal. And it's easy to manipulate it, probably because it's a smaller field, and the smaller the field, the easier to manipulate things. So this is, and then there is also the ongoing problems with refereeing, how it's.
So what extent the IMU plays a role in deciding, universities decide on what publications they buy?
The IMU can make recommendations, can come up with recommended practices in, for example, how to evaluate a researcher or how to evaluate a journal. One has to be very careful, but I think the IMU can promote. That I think you could do and should do is to promote the free electronic journals by giving some kind of official stamp of approval, quality, something like that, so that researchers have the alternative of publishing there without saying that, oh, these are the second-class publications.
So it was done under your leadership, this kind of action?
Something was done. We came out with a report about impact factors and their misuse in evaluation of journals, and there are now other committees trying to come up with reports and recommendations. I mean, you cannot do much more than do recommendations for the practices of the universities and other institutions.
Another thing the IMU is doing is we're basically sponsoring the prizes that the mathematical community gives. What do you think about prizes in general? Do you think that they are good for a field or not so good? There's no doubt that they create controversy each time.
I think a certain number of prizes are good. It creates some public interest for the field. It is a way of recognizing some of the key research directions. I think I don't mind to have some prizes which everybody recognizes that these are central. And there will be, of course, I mean, one has to have the understanding that there will be people who are as good or maybe even better than those who get the prize, who will not get the prize. So not getting the prize doesn't mean that you are not good enough. And I think that usually, like with Fields medals, usually people who get the prize, they deserve the prize. They are outstanding young people. You can always argue that there are, 4 others who would be just as good and they don't get the prize. So you have to understand that this is the situation.
The people who don't get it have to understand that this is the situation. No, but I think they do.
I mean, that also their environment. It's not the end of the world if somebody doesn't get the Fields medal. I mean, for those 10 people who are potential recipients, they should understand that this is the case.
Taking the family and moving and living in a different country for long periods of time, in particular moving your children from school to school and from sometimes town to town and changing languages and friends and so on. So you obviously have done it. So what can you say about it?
I think it goes with our profession that every now and then we have to spend time at a different institution. At least I always found that it's important. You learn a different kind of way of thinking, a different set of problems. And also in education, you learn a different style, or at least you see a different style of education. You either accept it or accept some elements. So this is unfortunately for the family, that's not so easy. I mean, my wife always understood this. And of course, she's a mathematician. So she also herself took part in this experience. She herself went to seminars often taught when we went abroad. For the children, it's more difficult, I think, and I don't really know a good answer to this. We had all sorts of arrangements. I don't think the language is really the problem. They pick up the language fast. I mean, we went to German and English cities to spend longer time there, and they picked up the language reasonably fast. With the friends and culture, it's a little bit more difficult. I don't have a good answer for that. I mean, obviously they also profit something from it. I mean, just to pick up 2 extra languages at a level which you would not get in going to school in Hungary, that is already some substantial benefit. But it's sometimes hard on them, and there's sometimes nothing we can do about it.
Do they talk about it? I mean, with hindsight, I mean, now all of them are adults.
Sometimes they talk about it and they say it was unpleasant in some cases to have to move.
So you are a family of mathematicians, like you mentioned. You and Kati are mathematicians, and you have 3 daughters. Well, I know all your kids. Your daughters, I don't remember if they showed interest in math, but then your smallest son did. And I wondered when did you first recognize that he has mathematical talent?
Actually, my daughters also showed interest. I'm happy that they were not frightened away from mathematics, even though none of them has become a mathematician. My son, I think the difference was that while they were equally quick in, say, logical games or something like that, they were always more interested in social elements, friends, and then when they became came to their university studies, they chose to study something which economics or literature or something which had something to do with more human elements of knowledge. But my son, it was pretty clear already when he was 3 or 4 that he was good in mathematics and interested in this kind of things, and he also had the drive that these kind of questions and logical puzzles and logical computer games, they interested him by themselves, just for the logic of it. When he was in 6th grade, that was the last year of elementary school in Washington, and state of Washington, and the school said that they cannot really offer him mathematics education anymore because he already took the courses or was rushed through some other courses, and they offered that they would bus him to the middle school every day so that he can take a class there and then bus him back. And that I didn't like. This idea, I didn't think it was useful. I thought it would be disruptive. So I agreed with the teacher that I will take Hungarian textbooks for the 6th grade, and I will translate problem sets from them and give it to him. And he would sit in the class and work on those problems, and I will grade them, and that would be his math education for the year, and that worked very well. I also got into the mood, so I translated problems and sometimes added some more problems. And there's also a periodical for elementary school kids in Hungary, little bit like the traditional high school periodical, but just with simpler problems. And so I translated also problems from there. And it was about 2 months after this went on, he came to me and said, you know, Daddy, this is somehow not a just arrangement. And I thought that he thinks because he has more difficult problems to solve. And then he said, you know, all the other kids are sitting there and doing 20 multiplications every class, and I have all those fun problems to solve. And I said, but you did the 20 multiplications last year. Yeah, but still, I mean, this is his friends, and somehow. So I like, of course, this kind of problem solving more than doing 20 multiplications every class. I think it went quite well, and we both enjoyed it. But after that, I actually tried to stay away a little bit from him, from his education, because I think he should find his own way, not to be attached to me so closely.
So he learned by himself, things. So it was the summer programs at.
There were summer programs in Hungary where we went to. He also, whenever we went back, Lajos Pósa, whom I mentioned, was one of the prodigies, child prodigies of Erdős. He became then later interested in education, and he's running now math camps, and not only in the summer but all around, weekends and so on. And so he went to these, and also then for a while my wife ran a math club in Redmond, and he attended that. So we had we took some part in his education, but all in all, I tried to stay away from it.
Is he interested in similar problems?
Yeah, he got interested in similar problems, and that's because he liked. His favorite teacher was András Frank, who was my first PhD student, and now is a professor in Budapest, and so he got interested in combinatorial optimization problems, but it was with András Frank whom he worked a little, not with me.
What are the most interesting problems for you? Problems you tried hard to solve and you didn't, or you're still trying? Or?
I could tell some current problems that I find interesting. I already mentioned you that I would like to understand the possible limits of extremal graphs, fix a problem, extremal problem, and then how do the large extremal graphs look like? What is the template for them? This seems to me like a quite fascinating problem, and there are all sorts of conjectures concerning it, so it might even be doable. I worked on Hadwiger's problem for a while. I mean, I now confess, I worked on Hadwiger's problem, got nowhere. I worked on the problem of trying to find a combinatorial algorithm for coloring a perfect graph optimally. I got nowhere.
We are on camera, you know.
Yes.
Let me ask you about definitely a problem that is very close to my heart, and I'm sure you must have thought about it, given that you thought about this P versus NP question that was clear very early to you, the importance of it for understanding, let's say, graph theoretic problems, even if you are not interested in algorithms. So, so one question is whether you thought about it and you have any ideas about what you think the answer should be. And maybe more to the point, as a combinatorialist, it seems that the situation is that it can be formulated as, basically it's a cover problem, or it can be formulated as a combinatorial problem in many ways, for which we can't even begin to prove the first non-trivial bound, superlinear lower bound, let's say, even forgetting algorithms just as combinatorial cover problems. Do you know why? I mean, why is this set of combinatorial problems one which we cannot make progress on, whereas we seem to be doing quite well on lots of other directions in combinatorics?
That's indeed a surprising situation. I think that one possible explanation is that it's exactly because it's such a, it has such a connection or such an implication, such an impact on logic, on sort of the basic structure of mathematics, that it is so difficult. And sometimes I like to bring up the example of, suppose that you ask Archimedes how to construct a regular seven-gon. He probably would have said, well, I think it's not possible, but I have absolutely no idea how to prove something like that. And indeed, it took almost 2,000 years, or about 2,000 years, before it was proved that you cannot construct a regular seven-gon with ruler and compass. And not only that it took so long, but the tools that you need to prove this were developed in an entirely different setting. Algebra and real numbers and the notion of solving equations and so on. And then once everything like that was in place, this was actually a relatively not that hard theorem. But somehow I expect something like that happen with P equals NP, so that somewhere somebody will develop some tools, I don't know, maybe in probability theory, maybe in topology, maybe in algebraic geometry, and those tools, at some point somebody discovers that they will just imply that you cannot compute a Hamiltonian cycle in a graph in polynomial time.
But you don't expect this will be the situation with the Riemann hypothesis. So you don't think that in order to solve it, you need to wait for something in topology or in...
Sometimes I also view the Riemann hypothesis as a combinatorial problem. The core of it is you have to be able to say something about how the Möbius function, what cancellations occur if you sum the Möbius function, and can even generalize it so that it becomes completely combinatorial. You don't need anything integers, it's just subsets of a set, and you have the Möbius function on the subset, which is just -1 to the size, and you are summing it, and you have to be able to understand the cancellations that happen. So I don't think, it doesn't feel like so inaccessible as but then already to Riemann it looked like, just some lemma that you have to prove. So it's not, these feelings may be wrong, and maybe it is as inaccessible, and really you need something new there.
Yeah, I was reminded a particular formulation of the Riemann hypothesis is just estimating the determinant of an easily defined matrix, and this reminded me of another favorite problem, which I'm sure you thought about. I think it was you who first observed that computing whether a graph has a perfect matching can be easily done by just placing indeterminates for the locations of edges and zeros for where they don't exist in a matrix, and just computing the determinant of this symbolic matrix, or rather testing whether the determinant of this symbolic matrix is 0 or not. And you observe that while it may be complicated to do it symbolically, you can just plug in random numbers and just see what happens. This works in this case and in lots of other cases, but we don't understand whether randomization is essential in this kind of situation. So in particular, given a matrix whose entries are variables or constants, to tell whether the determinant is identically 0. Did you try to think about it?
Oh yes, I tried it a lot, and it's one of the. I mean, sometimes I think that it should be doable. You just have to come up with the right idea how to find a substitution, maybe by some algebraic trick or maybe by some combinatorial method. Sometimes I think, well, it's probably no. I mean, that problem should maybe be complete for randomized polynomial time or something like that. I think this whole issue about the role of probability or randomness is something that we still don't quite understand. One topic I worked on for actually several years was trying to compute the volume of a convex body in a high-dimensional space, and that's where one can prove. I mean, it depends on the computational model. So if the convex body is given by an oracle, say a membership oracle, it tells you whether a point is in there or not, then one can actually prove that randomness is much more efficient than deterministic algorithm. But if the problem is completely given in advance, then I'm not so sure about this. I know you believe that it doesn't help at all. I'm sort of thinking one way and the other day thinking the other way. I think it's one of the really crucial, fundamental, open questions in the foundations of mathematics, whether randomization gives anything more powerful in a situation where all the data are given than just deterministic algorithms.
So the reason for my belief is just that it's tied completely to the question of P versus NP. So you have to believe one of the two, either that P is different than NP or that randomization is powerful, but you can't believe both, because if we have lower bounds, then randomization is weak. So in particular, you mentioned the possible completeness of deterministically testing whether a determinant of a symbolic matrix is 0. We know it is. So we really know that if you find a deterministic, by result of Cabanes and Impagliazzo, if you find a deterministic method to do it, which is efficient, you immediately get lower bounds.
Okay.
It's partly maybe explaining.
I think this is something quite an important question, but which is sort of on par with P equals NP.
One injection of classical math to this discussion was this Mulmally program, which is using algebraic geometry maybe to resolve questions like P versus NP. Do you follow it?
I have not followed the details. No, I know about it. I tried to understand it on a high level, but then I didn't go into the details. I certainly will when it will produce a proof.
Well, we may have to wait a little bit for... But it is producing proofs of other lower bounds, at least on tensor rank. And
oh yeah, there's no question that's a fruitful idea. And something like that might actually bring at least some nonlinear lower bounds. I think at the moment this would be already a big success.
One problem that I think I'm very interested to know how you came to think about it and how eventually the collaboration went was your work on the short vectors in lattices and then the application to factoring polynomials.
This is actually interesting because it shows that sometimes how roundabout ways things arise. So I mentioned that we were writing a book with Lex Schrijver and Martin Grötscher. And the book was about applications of the ellipsoid method. And we developed some kind of general theory for it. And this theory had one point where we could not, at that time, were not completely satisfied with it, which was that it worked in the full dimensional case. So it says that if you have an oracle, that you have a convex body and you ask a point and the oracle tells you a separating hyperplane, then from this oracle in polynomial time you can optimize any linear function on the convex body. And this worked if the body was full dimensional, but if it was of lower dimension, then somehow it didn't work. I mean, and you could, of course, get around this because once you assumed anything else about the oracle, like it gives you a rational hyperplane and you also know a bound on the denominators of whatever it returns, anything like that, then it worked fine. But in the general case, there was something little was missing. Obviously, it was completely insignificant, except that there was some gap in our knowledge. And so I began to think about how to fill this. Maybe we could fix it. And then I managed to translate it into the problem of finding simultaneous Diophantine approximation for certain numbers. And basically, if you get a hyperplane that's returned and you want to round it to some bounded rational denominators, but if you work out how that you don't want the hyperplane to move too much so that it would cut into the body, and therefore you work out what the condition is, and it has to be a simultaneous Diophantine approximation in the sense of Dirichlet. And of course there's a classical theorem of Dirichlet that such an approximation exists, but how do you compute such an approximation? So I began to think about this, and I realized that it can be translated into finding a short vector in a lattice. And then I remembered that I heard a talk by Lenstra, who half a year earlier, by Hendrik Lenstra, where he had an algorithm for solving integer programs in bounded dimension in polynomial time, and this algorithm was depended on basis reduction in the lattice. But his algorithm, basis reduction algorithm, didn't work for when the dimension was part of the input. And so I began to think about how to do this in a high-dimensional space. And it's actually, in that problem, it's easy to come up with ideas, algorithms. And then eventually you see that the algorithm slows down. I wrote a little program on I think I had a Texas 59 calculator, and I wrote a program on it to check these algorithms on maybe simultaneous approximation of root 2, root 3, and root 5. And then I tried all sorts of variations. I mean, whenever I had an idea, and then one seemed to be much faster than the others. And so it took me maybe a couple of weeks, and then I was able to prove that it indeed works in polynomial time, and it's seemed to be quite fast. And then I wrote to Lenstra that I have this algorithm, motivated by his algorithm, but was clearly different. And then he wrote back that in the meanwhile, he and his brother, Arjen Lenstra, have noticed that if you can do this, then actually they can factor polynomials over the rational field in polynomial time. And so we decided to write a joint paper. I mean, that's how it came about.
When you went to Oberwolfach, you mentioned that Tarski invited you there, and he's well. There are lots of stories about him. What was your experience in interacting with him?
There was nothing unexpected. So he was very friendly, and I found him very nice. I didn't have so long conversations with him. He was co-organizing it with George Grétzer, and George Grétzer was a Hungarian, so of course I talked more to George Grétzer about these, whatever life in Hungary and all these things. But I do remember that he was very friendly and encouraging.
He was like a master of the concept. It was a logic?
It was a universal algebra, logic, and category theory conference, something like that. Yeah, he was obviously the main person there. And yeah, they were working on quite combinatorial type problems in those days. Somehow the universal algebraic aspects of finite structures. That's why he was interested in this cancellation law for graph products, which actually extends to any kind of finite structures.
Oh, there is a product which
there's a product. There's a natural product. Well, under some side conditions, which you have to assume, but it has this cancellation property. It actually extends to all categories which have a property that between any two objects there's only a finite number of morphisms. And recently I got quite interested in this kind of combinatorial theory of categories. I think it's a very unfortunately neglected area. I mean, in finite structures, you have this kind of categories. I mean, between two finite groups or two finite graphs, there's only a finite number of maps. And it turns out that there's a lot of combinatorics that can be put in a very natural form. And then lots of good questions are inspired by this. And you can try to study find this kind of categories, locally finite categories, for their own. I mean, it's just one step more general than a partially ordered set. I mean, every partially ordered set is such a category. There's only one morphism between at most one morphism between any two objects. So in this case, you have a finite number, and it seems, so for example, the regularity lemma can be extended to categories. There's a regularity lemma for categories and so on. I mean, this is all works somehow.
So that's a directed situation.
You are not partitioning the elements of the category. You think of a partition as a map of one graph into a much smaller complete graph, and you can translate this into categories so sort of you can generalize it to categories. There's a lot. There's only one. I mean, the Prague school has maintained this and cultivated this view. Neschet, Schiller, Poulter. They have this categorical approach to things, and I think it's actually quite interesting, and it should get more attention.
I think it's actually conflicts somehow with the description of combinatorics you gave when you described your high school experience, in which is very concrete and sort of down-to-earth problems which anybody can understand. And at the time, maybe mathematics, part of the reason mathematics was opposed or looked down on discrete math was exactly because of that, whereas they were trying to generalize and abstract everything. So it seems that here you are taking a view where, abstraction will, things abstract and we should do it.
This is rather down-to-earth situation when there is this finiteness condition on the category. It's really a very combinatorial object. And I think it's... I'm not saying that generalization is bad. It's just that things should be generalized so as to maintain some kind of non-triviality, some kind of essential. So as long as you get results which, when you specialize to the category of graphs, gives a non-trivial result, like a regularity lemma or maybe this characterization of homomorphism functions that we obtained with Mike Friedman and Lex Schreiber. This can partition functions. This can also be extended most verbatim to categories. So these are then you get for free the same result, same characterization of homomorphism functions for hypergraphs, for semigroups, for directed graphs, for whatever objects you want, because they are all form categories. In that case, I think it's the categorical setting which is the natural one.
We didn't discuss when talking about reasons somehow why discrete math sort of gained prominence and within more classical mathematics. And I think probably the regularity lemma played, once it was realized that you need it, played a significant...
The regularity lemma is almost, I mean, as most sort of the really important discoveries have many forms. So original form, it says that the graph, if it's very large, a large dense graph, the vertices can be partitioned into a bounded number of classes, so that if you take any two of these classes, then the graph in between them looks like random. So it's really, again, randomness comes up. Between different classes, it may be random with different densities, and there is a certain number of exceptional pairs which is allowed, and so on. But it turns out it has many other formulations. It can be formulated as a result about such a classical problem as approximating a function in two variables. It has generalizations to more. The two variables with a step function, where the steps are rectangles. And the crucial property is that this approximation number of steps only depends on the error bound and not on the function you are approximating. So it's a very fundamental phenomenon in approximation theory. And then it can also be formulated as some kind of I will not do all these formulations. Something about again, approximation in Hilbert spaces, and it can be formulated as some kind of result about finding typical sets of points in a graph, and so on, and it goes on and on. So it's something which has and then this is just the original lemma, and then it's extensions to sequences of integers, and it has extensions to hypergraphs, which actually was a quite difficult step, and it took about 10 years until people were able to come up even with the right statement of this more general lemma. So now it's sort of usually put in the form that every very large structure can be decomposed into so can be viewed as composed of three parts. One has a simple structure which can be described in a certain bounded way. It has a bounded description, and then you put on top of it a random structure, and you put on top of it some very small error, and you can apply this to all sorts of structures, functions on abelian groups or hypergraphs or many others.
Of course, Sem already used the regularity lemma in order to prove sort of van der Waerden conjectures, a problem of a famous mathematician about these arithmetic progressions in dense subsets of the integers. But it seems to be used for maybe 30 years only by combinatorialists. Of course, it's a very powerful tool and was used as such in combinatorics, but it seems that it made a breakthrough into the mathematics community when Green and Tao used, more sophisticated tools, but in particular of the same type of composing randomness and structure, when proving the same result, long arithmetic progressions in the primes. So, which is, I don't know, maybe you know more, may not be so interesting to number theorists. So can you explain the psychological, transformation, why it suddenly became important?
First of all, even in graph theory, it was slow how it spread, partly because the original formulation was rather complicated, and maybe graph theorists were not used to this kind of complications. And also you had to learn how to apply it. I mean, it actually has to be supplemented by a number of results. Like there is the blow-up lemma, there is the counting lemma. So these are results which you have to use in combination with the regularity lemma to really get those powerful results that nowadays almost every substantial new result comes from the regularity lemma, so or uses the regularity lemma. This problem of actually Erdős and Turan that about sequences of arithmetic progressions in dense sequences of integers, that really probably was considered by number theorists, maybe still is, as some kind of more combinatorics than number theory. Once it comes to primes, it's becoming more number theory than than just combinatorics. So really, I think you're right that the Green-Tao theorem was a very important step in making these kind of methods, integrating it with number theory. And there's probably more. Tao gave the opening talk at the Congress in Madrid, and then he explained that it's a very similar situation in differential equations and so on, where you have complication and you want to understand it by separating some kind of understandable structure from randomness and maybe a small error. I think it's this regularity lemma has also become fundamental in the limit theory of graphs, as we already talked about it, and I think I'm actually wondering when applications in analysis will come, because I think that if there is this kind of very surprisingly strong approximation result, it should have applications in analysis too.
I want to talk about another result of yours that's, again, very close to my interest, and I think it's one of the most fascinating connections that were made in computer science, and this is a connection between probabilistically checkable proofs, PCPs, and hardness of approximation. So can you talk about this and how it came about?
This is another example of things that came unexpectedly out of some different question. I was in Princeton and for a year, and was talking with Uri Feiger, and we were trying to understand how doing certain things in parallel, how does it relate to doing things in sequence? Whether, for example, two people play games on two boards in parallel, how does it influence the winning chances of one and the other? So there are many questions like this. And this is some kind of idea of trying to estimate. I mean, if you translate it, then playing games in parallel is really kind of a product, and you want to estimate certain parameters on a product. And the idea came up, this was the Shannon capacity problem, which was also a similar thing. So you have to take products of graphs, and you want to estimate the independence number of the product. And so the question was, can we do something similar here? So develop some kind of maybe some relaxation, some semi-definite relaxation that would be multiplicative, and that would then give an estimate on this kind of product game or product protocols that we were trying to understand, and somehow we didn't get too far in this, but at some point we realized that it's not only similar to the Shannon capacity problem. It is actually about trying to find a maximum independent set in a graph. And then at one point, Uri said, well, we're not getting ahead here, but maybe we can use it in reverse and somehow use the negative results, use the positive results that exist about sort of being able to do better on 2 than on 1, to prove that you cannot really approximate this, cannot really compute approximately this maximum independent set in this graph.
And now it's a general graph as opposed to...
It was a general graph. Of course, we worked it out, and it turned out that, you know, other people contributed, had similar ideas. So eventually, that was my role. Now, it has, of course, it's a long story, and it started earlier and ended earlier. So, I mean, there is eventually this sort of the paper of, is it Aurora, Sudan, and...
ALMSS.
Yeah.
Yeah.
Aurora, Motwani, Lund, Sudan, and Szegedi. Not Balázs Szegedi, but Mário Szegedi, where they get some very sharp result. But for that, you had to translate it to actually as a coding problem, and then find the right coding. But of course, this idea of coding goes back to the work of Babai, Fortno, and Lund. So it's really a progression which eventually got to this PCP theorem.
I think you can explain why the fact that there is a way to explain what PCPs are, and why should it be related to the hardness of approximating clicks?
Okay, so the PCP theorem is basically says that if you take, maybe I can talk about that, take any mathematical proof. Well, if I write down in a paper a proof and I give it to a referee, then the poor referee has to read the proof to make it sure that it's correct. And it's fairly sort of, well, I mean, everybody's experience is that if the author writes it out more detailed, then that actually makes the life of the referee easier. But now it turns out that if the author writes it out in even more detail, then the referee doesn't have to read the whole thing. The referee can read only parts of it, and in the extreme, the referee has only to read a few bits of the whole proof. And if those bits are okay, they are consistent with the claim that this is a proof of the theorem, then he can accept it that the proof, that this is, well, he can never state that this is a proof of the theorem because there could be some typo somewhere in the proof, but he could assert that if you fix the typos in the proof, then it will be a correct proof of the theorem.
It's an error-corrected version.
So it's really a coding problem. You take a proof which is of some length, and then you encode it into some bigger, longer proof, but it doesn't have to be that much longer. It's polynomial blow-up. And the point is that this encoding somehow contains the checks for the logical steps that has to be correct. It sort of, every logical step is distributed along the whole proof. So if you check some random points in the proof, and if there's any logical step is missing, then that would mean that all of them show up in this small sample, that all the errors in the proof show up in this small sample that you take. So this is one of the most amazing facts that there is. Why would this be so? And of course, it's pretty far from the original formulation, which was multi-prover proof system. Started by one of your papers with Goldwasser and Kilian and Benoit. Yeah. So I think that this whole area is really an example of a development where one result was building on the other, and eventually led to this very surprising theorem about PCPs. Now, why is this? What does it have to do with hardness of approximation? So, I remember that even in the maybe late 80s, it was I was talking to people in say operations research, and they said, well, we know a lot about exact algorithms, but nobody really knows anything about approximation algorithms. There are really no good methods, there are no really good negative results, no theory of approximation algorithms. There were a few sporadic things like Graham's approximation algorithm for bin packing, and there was even one or two negative results by Gary and Johnson about coloring, but they were really isolated examples. And then sort of around the early 90s, and all of a sudden these two things happened. The one was the Gomans-Williamson algorithm that established that sort of semi-definite programming is a strong method to obtain approximation algorithms, and then many were found. It's now a big area. And there was also this negative result. So it was somehow interesting because of this, so that all of a sudden there was a tool to prove negative results. So what does it have to do with hardness of approximation? It's because if you want to it's from the PCP, it's not so easy to see.
It's because the PCP works for any proof. So for any NP, you can write such a proof, such a coded proof for any NP complete language.
Yeah. So the approximation is that if you really want to approximate the probability of the error. I mean, basically that's so if you look at the proof and you could tell what is the probability that you see an error, so you can approximate it. So that's an optimization problem, and you could approximately solve it. Then from this you could actually get whether there is a proof. Okay, so you want to find an encoded proof which would minimize the probability that the referee discovers the error. And if it can be done so that this error is less than a half, say this probability is less than a half, then actually by the PCP theorem it follows that the proof can actually be corrected, and therefore the statement you want to prove is correct. So this is how an optimization problem is sort of behind this PCP theorem, and that's how then you have to start the usual machinery. You take some approximation problem, you want to prove that it's hard, and then you encode it. It's a little bit more tricky than in the NP case, because you have to preserve the degree of approximability, not just the exactness of the solution, but all this has become a very powerful method.
There was finally a gap between correctness and incorrectness.
Yeah.
Completely different question is about time management, and of course you are doing a lot, and everybody I talk to have no idea how you manage to do all the things that you've done, especially as you've in the last few years have taken both the presidency of the IMU and the chairmanship of being chairman of your department in ETVES in Budapest. And to me, the one thing that I found among the most mysterious is, when do you find the time to write books, which always seemed to me like a huge project that it's rare that anybody can do.
Books you can only write if you really decide that you will spend every spare time that you have on writing this book.
If you have it.
Yeah, if you have it, yeah. So I didn't write a book while I was the president of the IMU. And then also when I was at Microsoft, then I didn't write a book either because I was involved in research. And so now I started to write a book on graph limits, and I'm almost finished. The only way to do it is to have the support of the family or understanding of the family, so that they say, okay, it doesn't matter that you neglect me now for the next half a year. I know that if you finish the book, it will be different. So I got a lot of support from my wife, Kati, in this sense. I mean, that's the most. She's also reading the manuscripts and correcting them and doing a lot of help, also with technical issues and so on. But I think most help is that she understands that now I'm in a book writing mode, and that means that after dinner I stand up, I go to my desk, and I write a book for 4 more hours, and on Sundays I mean, sometimes she says, okay, let's have at least an hour of walk around or something, but basically she understands that I'm sitting there and writing the book.
But you started very early. I think that the whole generations of combinatorialists grew up on your book, which was a collection of problems and solutions, which I don't know, you must have, I don't remember how young you were. You can tell us what compelled you to do this?
I don't exactly remember when I started to do that. I was a student, certainly, but it was raised by my high school math teacher. And once we met him, I was Posha and Lackovic, Pelikan, and he said, well, you guys know a lot, so why don't you write some problem books in the style of Polyaszegő, which is this traditional analysis problem book. And actually, we all got enthusiastic and started to write it. And then eventually, I'm afraid I'm the only one who actually finished the book on combinatorics. You can measure how well you understand something. So you understand some material if you find that you would tell it entirely differently from how it is told in the paper. If you just can retell the proof or presentation in the paper, then you still don't understand it. But this also has a second half. I mean, once you want to do it, tell it in a different way, you usually don't have a chance. I mean, it's somebody else's paper. But if you write a book, then it's different. Then you can tell it in your own way. And I actually find this somehow satisfying. Not because it was told in a bad way. I mean, it's not the issue. I mean, it's just that I have my own way of looking at it, and it's somehow satisfying that now I can express this way. And so this is what to me makes books, writing books, sort of which motivates me in writing books.
And you found that it also fits back into research, the writing of books. Did it happen that?
Absolutely, yeah. I mean, there's so many questions. I mean, right now writing this book on graph limits, I have a long list of papers that I should write once I finish this, because there are certain parts which I worked out, and often I don't include them in the book because maybe they are not that central questions, or they just don't fit. I mean, I already have 500 pages, so I don't want to go longer.
So how do you see the balance of books and papers, but in your case, in terms of influence, let's say, on the community? What's more valuable to spend time on?
I like both, and I also wrote some textbooks, mostly in Hungarian. Of course, one writes many papers because one has results, and it's sometimes difficult to judge in advance. So probably large fraction of my papers will turn out to be irrelevant, and I shouldn't have bothered to write them. It's sometimes difficult to predict in advance. I have some papers which I didn't even want to write down, and they became somehow highly cited papers, and then I have also papers which I thought I was extremely happy when I got the result. I still think it's a very nice result, and nobody ever noticed the paper. So this happens. I think this is part of the of life, but probably I should say that with a book, if it's a good topic and you really put your effort into writing it well, then it probably indeed has some kind of long-lasting effect.
Yeah, I think it's certainly the way you write books, it has a long-lasting effect. Can you give an example of one of these cases where you didn't really want to write a paper and it became influential and highly cited?
For example, I found the inequality between fractional and integral cover numbers, which is indeed a simple thing. It's a half-page proof, but now I'm glad I wrote it down because it's something which people use all the time. But I didn't want to write it down. I forgot it. So I computed the inequality, the proof for it, and then I said, oh, that's too simple to write for paper. And then a year later, I wanted to, or maybe 2 years later, I wanted to refresh it, and I didn't remember the proof. And so I spent 2 weeks trying to reproving it. And then I decided that maybe it's not that trivial. So maybe it's worth writing down, because if I had to spend 2 weeks to recover this proof, then other people who would like to apply this maybe would also. I think eventually everybody can come up with the proof, but it's not entirely obvious how to do it. No, this was my other in the other direction. There was a problem of Galai about alpha critical graphs. That's graphs which have the property that if you delete any edge, then the independence number goes up. They have a very interesting, fascinating structure, so they are non-trivial. And at that time there were several. It was somehow became a fashionable thing to work on in Hungary. Hajnal had papers about it and others. And there was a conjecture that there is some kind of finite, there's a classification of them, and in each class there is only a finite number of such graphs. And when I eventually proved this, that there is indeed only a finite, it looked like it's sort of the big result. So many people have tried to prove it and so on. But somehow it finished off the subject, and nobody ever cared about this paper. Even some of the lemmas in the paper have proved to be useful elsewhere, but the result itself is a kind of end of the story.
Well, this sometimes happens when a problem is completely resolved. What advice would you give a young person going into mathematics about which field to choose, which is what will be the most successful or interesting or generate exciting results in the next, 20, 30 years?
It's not an easy question because I don't see any area now like combinatorics was when I was 16. That was sort of obviously there with lots of open questions, unexplored. I think it was the genius of Paul Erdős that discovered this. I mean, other people have worked on it too, but he was promoting this. That here are these questions. Shouldn't we know the answer? This is very basic question. How many sets can you give so that no three form a sunflower? You should know the answer. Or how many sets can you have k sets can you have so that any two intersect, and so on. And all these combinatorial questions were there. So I don't know of any similar area today. A little bit later, there was also the similar situation with lots of algorithms. I mean, how do you sort? How many comparisons you have to make to sort an element? Or I mean, these are very basic questions. Obviously, you should know the answer, and the answers were non-trivial. Sometimes not that terribly difficult, but not non-trivial. If I come from the side of applications, then I should say that actually I think I was very lucky to experience one of those periods when mathematics was sort of developing completely together with an application area. I mean, that was something similar with physics and analysis in the 17th, 18th, 19th century, that it was the same people who did both. I mean, was Newton a mathematician or a physicist? Was Euler a mathematician or a physicist? I mean, you cannot really separate these. They did the same things. And any discovery, any question in physics inspired a mathematical discovery, which in turn, and so on, influenced physics. And I was maybe not on quite that scale, but something similar with computer science and discrete math in maybe the 70s, 80s. I mean, if you look again, it's the same people who did mathematics and computer science, and they developed in parallel and influenced each other very, very, very closely. I would expect that biology and mathematics will be like that in the near future. So there should be some, but it's not completely clear what areas of mathematics will play a role. I mean, one can guess that information theory will play an important role. After all, life is about passing on information to your descendants. But there are so many others. Clearly, issues in geometry about protein folding and of course issues in networks, because after all, on many levels of biology, the units form large networks, and the structure and also the way these networks work are really not so well understood, but they should be. So I would say graph theory and theory of large graphs, and then theory of how graphs change and how various processes work on graphs in time, depending on time. These are all areas which I think have only sporadic results. So maybe graph limit theory is one of the first attempts to at least try to understand one aspect of it. But this is just about understanding the structure of a graph. Now, you put on, I mean, this graph has to work. There will be either material or information or whatever flowing around on this graph. The units will influence each other. Then the graph itself will change under the influence of what's going on it. And I think that this would also be a very important element of understanding biology. So I would say that there are some areas of mathematics that I would clearly recommend to anybody who would try to maybe apply this to biology. And I would guess that there should be some really really active period when mathematics begins to play a real role in biology. Now it's still sometimes a language, sometimes sort of a off-the-shelf method of solving some differential equation or doing some statistics.
That's in the applicative side. What about the classical math?
Actually, that leads to a difficult problem, because mathematics is becoming so large that it's really not so easy to learn. I have always benefited from knowing certain areas outside my own, and I feel that I don't know them well enough. And there are some areas which I don't know at all. I have never studied algebraic geometry, for example. We didn't have a course when I was in university. And of course, I have heard talks and I have a little idea of what's going on, but very little. And in some other areas, I had courses, algebraic topology and so on, and I found it very useful that I knew some facts. I think that's a serious question where educators should think about. Is it how to find a balance between teaching certain areas in depth, and how can it be maybe extended by or complemented by teaching some areas, so that people should have a feeling about what the point in that area is. So I don't know algebraic topology well, but I think it's important. It was important for me to understand that what does it, like, what's a fixed point theorem means. So what is the power of being able to show that there is a fixed point?
You probably know about this project of Tim Gowers and this Encyclopedia of Mathematics, which he compiled. I guess the point there, his point was to exactly try to do what you advocate, and about every subject in mathematics, write 20 pages, which So I told this to some of my colleagues here, and at some lunch conversations, some people from the university, and by the way, it's a wonderful piece of work, which I love. But the reaction was something like, what? 20 pages on elliptic curves?
Well, that's, some of these may be impossible. But in some cases, maybe it is possible to explain. I still remember, situations where somebody gives a talk and it's impossible to follow, and somebody else in 5 minutes tells the example that should have been told right at the beginning, and from there, okay, I can then understand that you're trying to do that, and what does it mean? But somehow there is this kind of simple example.
Yeah, the book is basically about that. Yeah, the simple examples that illustrate, the goals and some techniques.
I think that's important, and I don't. It's very difficult to teach. At least the expectation is not that. The expectation is you take an area and then you teach all the theorems down to the last epsilon and delta. And I'm a little bit missing this kind of thing that people will not have a view of the whole subject, whole area.
Going back to the education and mentoring system in Hungary for mathematicians, the things you experienced as a kid, what can you say about the differences in it, let's say now, after the Soviet Union collapsed and a lot would change in many ways? How was education affected?
I certainly don't see today that people at the university would have would devote so much time to dealing with talented kids. Of course, there are some who do, but not on that scale. There are probably many reasons. I mean, Hungary adopted the grant system, which means you have to have grants, but then you have to write papers, then you have to, go to conferences, and somehow people in the 60s had more time because the borders were closed, so there were no grants, so they really could devote all their time to mathematics and at least some of it to nurturing talented kids. So this is a little bit negative, but it's a side effect of course. The much more positive changes. The other thing is that in the 60s, to become a mathematician was really the sort of a very desirable choice for somebody's career. I mean, it was more or less known that it has a high level, so you could, when you do mathematics, you will not be in the backwaters of the world. And politics did not influence it; they didn't care. And in fact, therefore, they promoted it because
it's not dangerous.
It's not dangerous, and also it was unlike say physics, it didn't involve a lot of money. So it was difficult to compete on the level of equipment, for example, with the West. But mathematics didn't need this equipment, so it was this handicap was not there too. So therefore, there was many young people wanted to become mathematicians. So I think that the general pool from which to choose the best was much broader. Now I think there is still this core of I don't know how many 5, 10, 15 students every year who doesn't matter. They will become mathematicians. For them, it doesn't matter whether it's a desirable career or not so desirable career. They cannot imagine to be anything else. But it's a smaller group of students from whom we can select the best, and that shows in the general interest. It's sort of there are negative effects of that.
The quality of teaching also.
Yes, of course, because if you have more students or a smaller number of really good students, and the majority of the students are not really so interested in, they choose it by random, or they think that they get some degree in mathematics and then they can go and have their own computer firm or whatever. It's a less interested, less active, less group. Then of course teaching is slower. It's more difficult.